Hi, so today we are going to do the question number 3 of ISI 2019, which came in JRF PhD exam QEB Group A. So this question is of 25 marks. So I'm just sharing the question. So this is the question. Consider a simultaneous move two-player game where each player announces an integer between 2 and 100, both inclusive. If both players announce the same number x, then each of them receives rupees x. And otherwise, if they announce different numbers, say x and y, with x is greater than y, then the player announcing x receives rupees y minus k, and the player announcing y receives rupees y plus k. So the part A says model this game, part B says find the best response, and C says find all the Nash equilibria, and D says do the same exercise with k is equal to 1. So let's start this question part by part, then we'll have easy solution. So let's start this problem. So we can see there are only two players, that is n is equal to 2, and also there are the strategy set for player 1 is 2 to 3 to 2, 3, 4, 5, 100. Either he can choose 2 or 3, 5, 100. So these set of integers. Since the problem is symmetric, player 2 can also choose from this strategy set also. So you can see the strategy set also here. So now let's write the payoff function for player 1. So if suppose player 1 chooses x is greater than y, then he will get the opponent's bid minus some constant k if his bids if his bid is greater than opponent's bid. What if his bid is equal to the opponent's bid? Then he'll get the same amount, that is x. What if his bid is strictly less than the value of opponent's bid? Then he'll get the value x plus k, his bid plus some constant k. So since the problem is symmetric, I can also write payoff function for player 2 also. Now let's start with the best response function. So best response, before approaching to the best response, there should be some value k, which is given in the question B part. You can have the payoff function in terms of the value k. So the question says k value is equal to 2. So just I substituted the value of k here. So you can see I substitute the value k is equal to 2 in place of k. So these are the payoff functions for player 1 and 2 respectively. So you need to draw the best response function. So I'm writing the best response function for player 2, since and the problem is symmetric, so we can also replicate player 2's best response. So the best response for player 1 is a function of player 2's strategy. So you need to fix the value of player 2 strategy values, that is y, and then think what is the best way to maximize first player's best payoff. So starting with the minimum possible thing for players 2 strategy, so player 2 can choose minimum possible value is y is equal to 2. So let's start from this case. So what if player 2 chooses y is equal to 2? In what sense player 1 can maximize his best response? So what are the cases of player 1? So I write here the value of y. So I substitute the value of y in place of y. You can see 2 2 2 here. So just substituted the value of a value of y2 here. So what if x chooses strictly greater than 2? X can be 3, 4, 5, 6 up to 100. So but I get the payoff is the value of y, that is 2. 2 minus 2 is 0, but in this case I'll get 2. So this case is irrelevant because x can't be less than 2 because the strategy set started from 2. So my payoff function will look like this. So I get uh, by choosing 2 is 2, and if I choose greater than 2 I got 0. So my best response is to choose 2 if y is 2. Now do the same exercise if player 2 chooses y is equal to 3. Now what if y is equal to 3? Do the same exercise. I substitute the value of y here. You can see 3, 3, 3, and then substitute the value of y in the next part to get the payoff function. So if uh, I choose of player 1 choose greater than 3, like 4, 5, 6, so I get the value of y here. So I substituted 3. 3 minus 2, that is 1. If x is equal to 3, then I'll get the value of y itself, and the maximum possible value which is less than 3 is x is equal to 2, because I want to increase my payoff. So I want to increase x such that x has to be less than 3. So that is only 2. So basically I'll get 2 plus 2, that is 4. So here I can see 4 payoff is highest among all these payoffs. So by choosing x is equal to 2, so I can see if y is equal to 3, my best response or player first best response is to choose 2, because 2 gives 4 payoff. Now what if y is equal to 4? So simply do the same exercise, substitute the value of y 4 here. You can see 4, 4, 4, and then substitute the value 4 here to get the payoff function. So you can see the highest payoff is 5 by choosing 3. Why choosing 3? Because I want to increase my this payoff function by choosing x as much as I can, but it has to be strictly less than 4, but I can choose 3 here. So you can see 3 is my best response if y is equal to 4. So do the same exercise for y is equal to 5 also. So you can see y is equal to 5, 4. So basically we can see if y is equal to 2, my best response is 2. Then you can see one pattern here in these three cases. If value of y 3, then I choose y minus 1. If value is 4, then I choose y minus 1. If value is 5, then I choose y minus 1. So basically if y belongs to 3 to 100 integers, then I choose y minus 1. So this is my best response function. So since the problem is symmetric, you can also draw the best response of second player. So now to get the Nash equilibrium, you need to plot these two best responses, and where these two best responses intersect, that intersection points, those intersection points are your best Nash equilibrium. So let's draw any of best responses. So I picked best response 2. You can also pick best response 1. It's up to your choice. So I pick best response 2 to plot. Okay. So I drew the x-axis and y-axis and plot the values 1 to 100. Now you can see what if x is equal to 2. So x is equal to 2 here. Then my best response, or not mine, it's player 2's best response, which is what the value of y is 2. So at x is equal to 2, my value is y is equal to 2. So basically this is the point of this coordinate system, that is 2 comma 2 is the one best response. So this is the point, you can see one best response. What if x is equal to 3? Then the best response of y is 3 minus 1, that is 2. So at 3, the best response for player 2 is 2, to choose 2. So basically this is the point, we can have the best response of player 2. So now, and we can see the best response for player 2 also. If y is equal to 4, then best response is to choose something like here 3, and do the same exercise for y is equal to 100. The best response is 99. Y is equal to x is, if x is equal to 99, y is equal to 98. So I draw all the points and by join them by the dotted lines. So this is the best response for player 1, sorry, player 2. So since the problem is symmetric, we can replicate this graph in a symmetric way to get the best response for player 1 also. So this is the best response for player 1. This is the best response for player 2. We can see at this green point, both the best responses are intersecting. So this is our Nash equilibrium. So there is only one Nash equilibrium, which is 2 comma 2. So we can say that at Nash equilibrium, first and second person both choose 2. So hence our C part is done. Now let's start with part D. So what if k is equal to 1? So I simply substituted the value of k, which is 1, in place of k here, here and here. Now simply do the same exercise to get the best response for player 1, that is pick the smallest possible value of y. So if y is equal to 2, then just simply substitute the value y in place of 2. Sorry, simply substitute the value of y in place of y. So you can see if I substitute the value of y here, you can see the payoff function look like 1, 2, and it is irrelevant. This case is irrelevant because the x can't be less than 2. So my highest payoff is 2 by choosing 2. So my best response is 2, or first player's best response is 2, given the second player's strategy is to choose 2. So 2 given that y is equal to 2. What if y is equal to 3? So simply substitute the value y is equal to 3 here. You can see the payoff function then. So if y is 3, then 3 minus 1 is 2. X is equal to 3, this is 3. And if x is less than 3, then the value of x is the maximum possible value, but it has to be less than 3. So maximum possible value is only 2 here. So 2 plus 1 is 3. So I can see 3 and 3 both are equal and the highest among all these payoffs. So you can see by choosing 3 you'll get 3. By choosing 2 you also get 3. So basically you are indifferent between choosing 2 and 3. So to get the highest payoff, so here your best response is 2 comma 3, given that y is equal to 3. So do the same exercise for y is equal to 4, you'll get 3 comma 4. If you do y is equal to 5, then you are indifferent between 4 and 5. So let's draw the best response for player 1. Let's draw the best response for player 2 here. Okay, so basically you can see the best response for player 1 is y is equal to 2. That is 2, you can see here. If y is equal to 3, then you choose either y is equal to 3, that is either the value of y or the value y minus 1. So that is 3 minus 1 is 2, 4 minus 1 is 3, 5 minus 1 is 4. So the value y minus 1. So you are indifferent between both these values. So let's draw the best response for player 2 here also. This is the best response for player 2 according to the symmetry. I drew the best response for player 2 here. This is the best response for player 2. So according to the symmetry, just replicate the best response for player 1 also here. So you can see best response for player 1 is this, and but the green line says that two best responses intersect at these green dots. So this is my entire the set of Nash equilibria, because two best responses are intersecting at these points. So my Nash equilibria says that x comma y belongs to the set of positive integers such that x and y has to be equal, but less than equal to 100 and greater than equal to 2. So this is the solution of this question. I hope you find it easy. Thanks for your patience and all the best for the ISI. Thank you.